Hi, so my name is Roland Bock, and I'm a principal software engineer at PPRO Financial Ltd. I'm also the author of several libraries. The probably most well-known is SQL++11. That is a library that we're going to touch several times during this talk as an example of the techniques that I'm going to present. I'm also author of a library called KISS templates, which is probably not that well known, but it's a library that allows you to write templates like in, I don't know, for instance, PHP, but with the usual type checking and name checking and whatever you have in C++. Right. Today I want to talk to you about how to test static assert. And many people just ask me, what the hell do you mean? What do you mean test static assert? Static assert itself is something that is used for testing. So let's first take a look at an example of how a static assert is used. So this is an example of some user code using SQL++11, as I said. So this is an embedded domain-specific language for SQL in C++, and you can express SQL statements as C++ expressions. Okay. And in this case, it's an update statement. So we update some table tab and set the name to whatever, in this case, John Doe. Looks innocent, but the library is a bit unhappy with this because the library is all about checking at compile time whether everything is right. In this case, it says, well, there is no condition here. We update everything unconditionally. That is potentially an error. And it tells you so by saying something about a return type or some incomplete type void. Okay, that's fine. But it also says you should call where or a function called unconditionally to either indicate what the condition is or that you actually want to update everything unconditionally. Okay, and the static assert says so. And that's one of the popular uses for static assert. You create you have tests at compile time. They produce hard errors, and they yield handwritten error messages, which are hopefully useful to the user in order for them to understand what they might have done wrong. Okay, but this is only really cool if the conditions are exactly right for the static assert. If you get them wrong, then either it doesn't compile if the user is doing everything right, or it does compile if the user is doing something wrong. Right? And then also you have to take care about the message. I won't talk about the message in detail. The important thing is to be consistent in the style of your message, I think. But otherwise, the condition is the important thing here. And to make things even more complicated, so not even do we have to figure out whether everything is okay, but there's also this issue that I received a few months ago for the connector library for SQL++11 from someone who used the Microsoft compiler, so MSVC, and for the same code that I showed before, Microsoft just says, well, variable cannot have type void. Okay, that is not very helpful. And the static assert is gone. And I didn't believe that, and my first reaction was, please show me the full error message. But this is, in fact, the full error message. That is everything you get from the same code, with the same conditions, only a different compiler. So the static assert is gone. And this is perfectly legal because the standard says, if a program contains a violation of any diagnosable rule, blah, 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 a confirming implementation, that is the compiler, shall issue at least one diagnostic message. Well, yeah, so it's legal. There are two diagnostic messages possible here. The other compilers give two messages. Microsoft's compiler just chooses to throw one away, the useful one in this case. Okay, so that's bad. That means static assert is cool. It has all these properties, and we can use it in fantastic ways. But yeah, sometimes conditions might be wrong. Sometimes it goes missing, so it needs to be tested. So in a sense, you can say we're testing our tests, and from a library author perspective, this is even, since my static asserts make sure that your code is correct. So I'm providing tests for your code, and I'm even trying to test the tests for your code. So that is several meta levels, but it's fine. Okay, so the goal for this talk, I want to assert that all my static asserts actually fire exactly when they should, right? And well, as a side goal, this would also be fine if I could test that MSVC users actually also get some useful information. Good. So here's some basic approaches. If you go to Stack Overflow and search for how to test static assert, you might get something like this. So first, code steering. I mean, because you cannot test it, that's one popular answer. You have to just do code reviews, basically code steering. And many people just do that. And I have to admit, in the past, that was also one of my approaches for this. At least for the part where you want to make sure that the static assert actually does fire in the bad case. The good case is easy, right? Because you just write test code, everything that you think that should compile, and if that compiles, then you have one side of the test already done. But the bad part, making sure that it doesn't compile, well, you do some manual tests maybe, and then some code steering, and then you're done. Okay, well, not too good. Another option that is also suggested several times in Stack Overflow is something like this. So you translate the static assert into a runtime assert. Okay, that is probably not a very good idea, but seems to be popular. Or doing something like this, so you translate the static assert into throwing some funny exception. But yeah, everybody knows that here, hopefully, in the room. Static assert most, or very often used to protect you from something that wouldn't compile anyway. Right? So translating that into runtime simply doesn't work. Okay, so since there's a compile time error, we can just compile code and see if the compiler fails to compile. That is a typical unit test, right? So you have something that is supposed to fail. The program that you test in this case is more or less the compiler, and the compiler should fail with the code that you presented for the test failures, or for the test cases that should fail. So here's some CMake example. I won't go into much detail, but the idea is I have a function that I can call with a file name and some pattern, some text pattern that I expect from the static assert. And then I use make test. Make test calls the compiler with the appropriate attributes, and the test is successful if this text is found in the error messages. Okay. This is one of these test files that I have, and I have a bunch of those. You can see the blue line is the one that we want to test. In this case, you have an aggregate function max, and somebody calls max on this aggregate function again. So that is illegal in SQL. The library is supposed to catch that, and it does. But it's a bunch of boilerplate nonsense that you need just for this one line that you're really interested in, and then you have to test that with a regular expression and see if the static assert is actually fired. That is a lot of work for just one test. And I have about 100 static asserts in my library, and I would like to do, I don't know, 20, maybe even more tests per static assert, so I would end up with like 2,000 or maybe 3,000 of these files. That doesn't really scale, and I'm not going to do that. So then a suggestion when I handed in this talk from one of the reviewers was, well, compiler developers need to test static assert. It's a compiler feature, so they have to have features or tools to test that. So yeah, and one which is very openly available is Clang diagnostic messages. You can actually annotate a piece of code with the messages that you expect the compiler to generate, and then with this funky command down there, run Clang, and then Clang will compare the messages that it's actually generating with the ones that you say that you expect it to generate. That is nice. And it is certainly helpful, and there are a bunch of test files in the Clang repository to do exactly this. One thing that you notice is that the expected error, even for this very simple thing here, doesn't even fit on the slide. And if you had reasonably complicated template code, then this line, if you put everything in one line, would go, I don't know, outside of the building. So, well, you can use Clang format and put it into something more readable. But then the compiler says, well, I don't understand what you're saying. It doesn't match. Okay, so this doesn't really work. So I don't know, for practical purposes, I wouldn't use that. And of course, it depends on the exact compiler version. And yeah, as I've shown, it breaks if you're using your normal tools. Good. Well, not good, but even if we used something like this, does this work in real life? I already indicated that, well, I mean, you would have to have many test cases anyway, and would probably take forever to compile all these. But let's take a look at a real example, or a very simplified example, I should say. We're going to use this example throughout the talk, basically, with very little variations. So let's try to understand what's happening. We have some struct A that has a function bar, returns void. We have a template function foo that can be called with any type. And the author of the function thought, well, it would be probably very good if this type T would be either A itself or somehow derived from A. Okay, and we test this with this std is base of. And if this condition is not fulfilled, then we fire a static assert and call t.bar afterwards. Okay, and then we call foo with an int, which of course breaks, right? And when we compile this, and we see the typical output from compilers like GCC or Clang is like this. You get this static assert failed with the string of the static assert. And then just to be sure that you know what we're talking about, it tells you, okay, this is a static assert with this condition, and the message again. So you have the message twice. But that is not true for all compilers. Sometimes you only get once. So MSVC only shows you once. And then the compiler carries on. It doesn't stop there, even though it's a non-recoverable error. Right? So at least Clang and GCC just continue and say, hey, and by the way, you can't call bar on an int. That doesn't make sense. On the other end, I don't know, I haven't tested this with MSVC. In some condition, you've already seen this doesn't happen because it stops after the first error. Okay, so if you want to really make sure that everything is fine, there's a lot of ifs and whens in order to really analyze this and make sure that everything is okay. Because different compilers do different things, and they might carry on. So if you wanted to do multiple tests in one file, which would be much easier and much more test-friendly, much more believable that somebody would actually write those tests, I wouldn't want to write the patterns for this kind of stuff to make sure that actually the correct lines really fired and not the incorrect lines. So, and then there is another case, and this is a function as it was about 1.5 years ago in SQL++ 11. This is the representation of the from clause of an SQL statement. The from clause takes a bunch of tables, and well, you have to make sure that everything is actually a table, because just by saying this should be a table, it doesn't make it actually happen that this really is a table. So you have to test it. It's tested in the static assert. Everything is a table, okay. And then we also have to make sure that the table names are unique, because otherwise the from clause is illegal. If you have tables, multiple tables with the same name, that doesn't work, okay. But there's a good chance that the second static assert doesn't even compile if the first static assert fails. And then you're in trouble. And I wouldn't even begin to try to get this right with either a build system or with the diagnostic messages from Clang. Okay. So we need to do something else. And the first step is to clean up the mess. We have to get rid of some of this nonsense that the compilers generate. And there are two techniques that I presented earlier and others presented earlier in other talks, so let's get quickly through them. The first is tag dispatch. The idea is that you move the implementation of your function into another function called whatever your function name is, _impl, or you can with any name that you choose. So in this case, foo impl. And you give it another parameter that you use to dispatch to these functions. In this case, I have one that takes a true type and another overload that takes a false type. The true type version does the normal body, and the false type isn't even implemented because we don't need it. It's only going to be called in the fail case anyway. And the function, the interface function that you documented in your API, then contains the static assert with this condition, and afterwards directly dispatches to one of these two impl functions. Okay, makes sense. It uses the same check and is either true or false. So if the static assert fires, then the second impl function will be called. Yeah.
There's no problem that the false type case doesn't have a body?
I'd say it's. The question is if it's a problem that the false type has no false case doesn't have a body. I'd say it's even helpful, because if for some reason the static assert is turned into a C assert or something like that, somebody does something very stupid and the static assert doesn't fire, then at least the linker says, well, this doesn't work. So it's a
compiler if you set it equal to delete.
You can also do that, yeah. Right. Okay. Otherwise clear? Tag dispatch? Okay. Good. What I just said that these follow-up errors don't happen is not exactly true in the case the return type depends somehow on the template argument. If that happens, then there is a good chance that the return type doesn't even make sense in those cases where your template arguments are bad, right? So in the bad case, well, then you would, in this case, so if we write it like this, then you would still get all the error messages from trying to construct the return type. Which means that the second step after tag dispatch that we have to do is we have to change the return type for the bad condition. And I don't know, in SQL++ 11 I use something that's called bad statement, because that is also an indicator, well, that your statement is bad. It's all about statements in that library. Okay, so we do something like this, basically the same functions as before, but instead of giving the same return type, we're now returning bad statement. Okay, and then we have to do decal type, or you have to use decal type to determine which function is actually called, to determine the return type. Just in case you're wondering, with C++14, there's this funny feature of determining the return type automatically, or let the compiler do that. That won't work, because in order to do that, the compiler looks into the body of the function, and there's the static assert. Okay, so so in that case, even the decal type would already break. Right. So when we use this code, and we're doing something stupid, so we call the function with an int, and then we do something with the result, something that is also not working because it's broken anyway. Then GCC and Clang say okay, well, there's no XXX in bad statement. Okay, that's expected. And there's also the static assert, so everything is cool. MSVC says, well, there is no XXX in bad statement. Okay, so we suddenly reproduced this, even with this very, very simple case, the situation that MSVC doesn't give us any useful information at all, okay, because that is all that we get. All right, and well, okay, we were able to clean up a bunch of the mess, but well, we're still not closer to actually testing the static assert. And we don't know how, we cannot somehow access the static assert inside the function. It doesn't work. So what we have to do is we have to well, do something different. And I want to show you how to actually make it testable. So what do we really need to do in order to test whether the static assert is firing or not? Well, there are two things. First, we have to test the condition. We need to make sure that the condition is right. And the other thing is that we have to make sure that the static assert is actually kind of linked to calling the function. Okay? And when you think about this, there's nothing that says that static assert actually has to be inside the function. That is not required. Okay, so what we do is we reorganize our code a bit, and so I'm trying to describe what we are going to do in the next few minutes, and then I break this down into simple steps, and then we'll see how this magically evolves into something that is actually making static asserts testable. So the idea is that, well, we have this conditional static assert. Static assert has a condition, and it's sitting somewhere. We break this apart. So we take the static assert, rip the condition out, and make it unconditional, but wrap it into some type, so that whenever we touch it, it automatically fires unconditionally. We take the condition and use it to construct a type that either is this wrapped static assert that always fires whenever we touch it, or is something completely harmless. And then we use this type that is now conditionally either dangerous or not. Then we use this type for the tag dispatch, and also as a return type, which seems to be useful. Okay, that's what I just said. So let's do that step by step. First, we define a small helper, and I don't know if you've seen earlier talks of mine. This is always coming up here because it's a very useful thing. It's a template that takes some type, and it has a value. The value is always false. Only the compiler doesn't know that, because the compiler has to assume that, well, maybe some fine day somebody will create a specialization for this type, which hopefully nobody ever does. But in that case, who knows what the value is, or even if there is a value. But for our purposes, it's always false, and it's cool that the compiler doesn't know about it, because that means we can use it to create a static assert in a type, in this case in the constructor of a type, that always fires whenever this type is being used. So we have a struct that we call basically what it's supposed to represent. So it's assert arg is derived from a type. It has a constructor with a default template argument. So it's a default constructor, and you can call it just like that. You don't have to provide any argument. Again, the compiler doesn't know that. It doesn't know how you would call it. And therefore, it doesn't know what's happening inside the static assert. The static assert is always false, you know that, but the compiler doesn't. So we now have, I don't know, something equivalent to a landmine just in C++. Whenever somebody constructs this thing, he or she will get a static assert. All right, we also need some counterpart. In this case, I just call this class OK. It is empty. It has a compiler-generated default constructor that doesn't do anything. In particular, it doesn't fire a static assert. And then, as I said in the beginning, we'll take the condition. This is base of A, and depending on the type, this meta function checkarg will either return an OK or this wrapped static assert. All right? Okay. And then we change these impl functions a bit. We don't do the tag dispatch on true type and false type, but instead we do the tag dispatch on OK or anything else. Right? And anything else is, in our case, then this assert arg is derived from A. And we use this both as a parameter for the function to determine the overload and also as a return type for this function. And in the interface of your library or your class, you do the same type with Decal type, same thing with Decal type as before. Only in this case, you call the constructor of this checkarg. And then you call the function with checkarg. Right. Okay, so this looks kind of similar to what we did before with the true and false, with a different return type. So first of all let's test if everything is still okay, that we didn't mess this whole thing up. Okay. Right. So two test cases getting rolled here. The first is the well-known not functioning, and the second one is the one that works. Okay, that's good. And yeah, sure, GCC and Klein say, well, XXX is not a member of assert arg is derived from A, and there's also the static assert, so that everything looks fine like before, and the good call doesn't cause any messages that is expected, so that's fine. And MSVC, well, it still doesn't report the static assert, but at least we now have a return type that is somewhat useful. Okay? So even for this crazy situation that the static assert is gone, we have some information that the user of this compiler can use to, I don't know, look it up in the code, which should have happened, or you could document this or whatever. This is useful, so it's not just lost information. Right. And if we ignore the return type, so if you don't try to call a member function on it, or if you don't try to forward it into the next function or whatever, then MSVC also says, well, there's a static assert here. There's this C2338. I think that's code for static assert. And yeah, and also mentions the type, so everything is fine. So all compilers behave reasonably. We haven't broken anything. We have improved the situations for MSVC users. What else? So let's take a look at the return type again. The cool thing about Decal type is that it, and I cannot give you that in standardese, but it really stays on the surface, let's say, of the expressions, and so it does only go as deep as really necessary to understand what the type is that you have here in your expression. So in the red part, it takes a look at this checkarg of T default constructor, and it knows, well, that's going to yield an object of this type. And it doesn't look into the implementation of this constructor. Therefore, it doesn't run into the static assert. Okay. And then it can choose the right overload. The overload is also uncritical. It doesn't have a body which could contain anything dangerous. It just returns something of this type. That by itself is also not dangerous. Nothing happens. So it will just say, okay, in the failure case, well, the return type is this. Which means that when we actually call the function, we run into the static assert. But if we analyze the return type, well, then everything is golden, because we don't run into the static assert and we still know what's going to happen. Okay, makes sense? So that means we can write tests like this. Okay, so in the first line is we call foo with some valid argument. Okay, and we can use same and static assert to make sure that the return type is as expected. We can also call foo with something that is not okay, and we can use isSame and static assert to make sure that yes, that is the type that is expected, because we know that this one contains the static assert that should be fired when we call this function this way, and we've tested that this actually is going to happen, right? So this means that we can now use static assert to test static assert, which is weird. And when I first thought about it, well, this is not possible because static assert is a hard error, so you cannot normally use it for testing static assert. But by using this indirection, it's possible now. So yes, we can use static assert to test static assert, and it's one line per test, and we can have hundreds of tests in one file, and it's really convenient to do that. Okay, so we just changed a little bit of how the static assert is linked to the function. Yeah? Where we don't have it directly in the function. Instead, we just move it out of it. Okay? And suddenly it's trivial to test whether everything is fine. All right. And I love this one. So I migrated lots of the static, not all of them yet, but lots of the static asserts in SQL++ 11 to this pattern, especially to get less complaints from Windows users. And when I did this, I created a branch, ran exactly this example on MSVC. First Clang. Okay, so Clang still does the useful thing. So it says something about the static assert and says, well, this is happening in the constructor of this assert where or unconditionally called. But MSVC says, well, there's a static assert here, and it's happening in the constructor of this type. So I have no idea what's happening. I have no idea what the logic behind is. I will not invest even a minute in trying to understand why this is. But for some reason, now I even get the static assert in MSVC. I have no idea why. I don't know, maybe it's about code complexity, but it didn't really change much from the old implementation to the new, whatever. Good, so short summary of what we've seen so far. So first of all, you should clean up your functions where you use static assert. That is, I think, a must. Use tag dispatch and failure return type to reduce the amount of error messages that users get. And then if you want to test static asserts, which I think is a very important thing to do, then, well, split your conditional static asserts into a wrapped unconditional static assert and a conditional type that is either harmless or this wrapped static assert. And then we use this conditional type for both tag dispatch and in the bad case as a return type. Then we can write straightforward compile time tests for all the static asserts. Very simple. And if you remember this funny from function with multiple static asserts, well, that's easy too, because and it's much cleaner than it was before, because this technique with using std conditional, or you can write your own equivalent of that with std conditional, you have one condition and check whether it's okay or it's the failure type. And you can chain this internally. So you can chain multiple conditions with multiple different wrapped static asserts. So depending on which condition fails, you can deliver individual error messages, or you can put everything into a tuple and make everything fire. It's up to you. So you have a much greater flexibility of what you want to give to your users. I tend to just say one thing at a time, but you have the flexibility to do whatever you want, and it's all still testable in the same easy way as I just demonstrated. Right. Now this is all very, very cool, you have to do one thing when you use something like this is every now and then you should write a unit test that makes sure that the compiler actually fails in the way that you expect, just to make sure that your mechanics for all of this are actually correct. Right? Because, well, if you modify it a bit because you think that well, this old approach is a bit I don't know, maybe it's not performant enough, compile time performance, and I want to do something better, you have to make sure that the compiler actually fails in the way that you expect it to fail. But of these tests, you need just a few, and the majority of your tests you can write in this way. Okay. Yeah, have fun with that. We can continue with either questions, or I have some bonus material about how this might look like in the future with future features. Okay, question.
Can you show us the macro that you used to make all this happen? In a previous slide, you had a macro that used SQLPP.
Okay. Okay, so the question is if I can show the macro that is used to create these things. Well, I don't have it here right now, but the macro is trivial. The macro takes two parameters, a name and a string, and the rest is always the same. So the name is the name of the type. The string is the message of the static assert, and since it's unconditional, you don't need to pass any condition into it. All of these look the same.
So you use that macro in conjunction with writing the condition in your code?
Yeah, so the question is if I use this macro in condition with the conditional thing, yes. So I have one line basically constructing this unconditional wrapped static assert, and or maybe multiple to create multiple of those, and then I have a battery of conditions linked to these wrapped static asserts. Richard, you had a question too.
Yeah, just a thought. So one thing I do about my static asserts is if I write them, sometimes I don't really want to add a string. They just kind of want to scale, and that's an extension C++ 17. But does that potentially lead to lack of error message for me later? My sort of is, would you recommend against not supplying messages? Am I farming my future use?
Okay, so the question is, what about messages in static assert? And C++ 17 explicitly gives you the possibility to omit the message. And, well, you've seen even code in one of these slides where I omit messages as well. Here we are. So for things like this, where you just write tests to make sure that your library is okay, and basically you use static assert to test your code. I think that's cool, because I mean, what do you want to write in there? Like this is a type requirement or stupid things like that, and you would always repeat the same message. It doesn't give you any value. So for those, the new feature is cool, and until then I would just use empty messages. But otherwise, if that is basically part of the interface, and you want to have static asserts to tell users that, hey, you're using this code in a way that is not intended, in those cases I would always get a message in there. Okay, so if you want, I can go to some future material. I'm not 100% sure about this, because this is not the other stuff is used in production ready code. This one here is just I don't know. I did some experiments, and this is what I think that we might end up with. So const expr if is something that is almost certainly going to come in C++ 17. It's a funny name for something that is written if const expr. And if const expr works like this, so you give it a compile time condition, And then, depending on whether this condition is true or false, one or the other of the blocks is executed by the compiler, is compiled actually, and the rest is pretty much ignored. Has to fulfill some condition about, I don't know, basic syntax checking or something like that. But otherwise, it is ignored. And so, if you forget about all the testability, this is very tempting, right? So you have this check arg of t. You can use a using to make sure that you only have to write this once, because maybe this check is something like this big and you don't want to repeat yourself. And in all the previous examples, you had to write the check at least twice. Here you can just use an alias, a type alias for the check, and then you say if const expr check : value, assuming that the fail cases all have a value of false and the OK has a value of true. Then, in the good case, we just call the function body as it was, and in the bad case, we return the check, which will then fire the static assert. Okay, so that is awesome in terms of expressiveness. Right? I really like that. And it's one of the reasons why I say that, Bjarne was unhappy about the features that come into C++ 17. I think they're very, very cool features, and I'm pretty happy with what's coming there. But in terms of testability, here we, in order to make this work, we use return type deduction. And as said before, return type deduction means that the compiler goes into the body of the function. In the bad case, it will run into this default constructor of check. And return type deduction works slightly different than decal type for whatever reason. I didn't really understand the standardese for that, but all compilers agree on that. And it runs into the static assert, just for detecting the return type. So we cannot test it this way. So what we have to do is something slightly different. So instead of having the static assert in the return type, we now use a compiler-generated return type, which does nothing. So this is totally harmless again. And we use just some randomly named static function. Again, it's a template function with a default template argument, so we don't have to care about it. And this fires a static assert. Okay. And then nostalgia, using bad statement again, like I did before, but this time as a template. And this template can be templated with one of these wrapped static asserts. And in the constructor, it will call this static function that we have now in the static assert. So whenever we construct this bad statement, then it will fire a static assert. Okay. And then we need something for return type magic. So we create a conditional type that checks whether this is the return type of something else, whether that is one of these wrapped static asserts. They now all have to derive from something or have to have some tag or whatever. They have to have some marker that makes them detectable. So let's use Isbasov in this example. And if they are one of these wrapped static asserts, then we construct a type of bad statement of t. Otherwise, it's just t. Then we can use that. Now the impl function is exactly what we've seen before. So this function that is so nice and expressive and easy to read and easy to reason about. And now everything is fine. Well, if you call this function, you call the constructor of check. The constructor is harmless now, so this is all fine. So when return type deduction kicks in, nothing bad happens. Then the return type of our interface function uses this make return type meta function which just calls this, that just uses Deckel type or operates on Deckel type for our foo impl. If it's the good case, then the return type stays as it was. If it's the bad case, then we wrap the return type into bad statement of this return type. And if we construct this bad statement return type, then it will fire. Okay, so in the last line, in this return foo impl of t, this will be used as an argument for the constructor of the bad statement of t. Okay, makes sense? And that constructor calls this static assert, calls this the static function of the rep static assert, and that will fire. Okay. Yo.
Why does it cause the static assert function to be instantiated and cause it to fire? Like why does that static assert come into the picture? Oh, sorry, the static function into the picture.
Okay. So the question is, why does the static assert function come into picture? So that is the constructor. The constructor takes one of these rep static asserts as an argument. Okay. And then we call the static assert containing function on this type. Okay. And in our interface function, since the return type is a bad statement of this rep assert type, and the constructor of that is implicitly converting a rep static assert into this bad statement. The constructor is called and will then fire the static assert. Make sense? Okay. Yeah, so I like this a lot. And when C++17 is available and I finally migrate my library to that, I probably will use this pattern. Because once you establish this, it's easy to use, easy to understand. And compared to a lot of other nonsense that has to be done in this library, this is really nice. Okay, so yeah, no, you don't have function overloads. The check only needs to be called once. That is a very nice feature, and so no possibility of typos there. Right, and then we have concepts. Concepts light, hopefully in C++20. This is not the use that I know Andrew Sutton and Bjarne Strustrup have envisioned. But if you prefer to have the messages from your static assert, then this is one way to do it. Okay, so we have two overloads now of the interface function. One requires that the check that we do on the template arguments yields true, so everything is fine. Then we do just whatever we want to do. And in the other case is just the fallback case. So it doesn't require anything, so that is less specific. It will only be called if the first overload doesn't match. And in that case, then we return check arg of t, which then has the desired behavior. Okay. So this is if you want to keep your static assert messages and you're not, because maybe you're not happy with whatever messages the concepts light implementation of your compiler will generate, which I think is likely. Right. Okay, so yeah, and otherwise, well, if you don't use a technique like this, then you have to find out how to test your concept light enabled functions. But I think that should be pretty much straightforward if you're into this kind of stuff, because that actually can be done with Svinay. So you're back to stuff that you can wrap a bit up, and then you're back to one-liners. But yeah, for this you have to be happy with the concept errors of your compiler. All right, more questions? Yeah.
So for each static assert you have to create your bad statement, good statement, and other structural assert to break down your food for each of your static asserts, 100 of them. So is there a way to generalize this? Because all you care is I have a function and I have my condition I want to test. So did you try to go in that direction?
Okay. So the question is basically, can I reduce the amount of code that I have to write to create all these static assert cases? So, and one of the questions, or part of the question was, what about the OK type? Do I have to have several versions of those? No. So for the OK type, I just have one. Okay, for all cases. For the static asserts, the wrapped static asserts, I have this macro, so it's a one-liner, but that will generate a bunch of code, will generate a bunch of structs. And as far as I can tell, there's currently no way around this, and I'm not aware of any proposal to change that, because the static assert, or the message of the static assert has to be a compile time string literal, and I'm not aware of any way to moving those around or to have those as template arguments or anything like that. But in the end, I mean, the difference isn't that dramatic. You have to provide the string in some way anyway, because regardless of whether you write a normal static assert or this wrapped static assert in a macro, or maybe later somehow in a template, you have to write this message anyway. You have to write the condition somewhere. If you organize your code a bit to work with this pattern, the amount of overhead is very low for this technique, and the gain is enormous, because you now have the ability to test that this static assert stuff, which is part of the interface that you're providing, is actually working the way it should. So for me personally, this is totally justified. But yes, I have to write for every single static assert one of these classes, and they have to be injected into some conditional or similar things. Cool. Yeah.
Could this technique be adapted to test static asserts found in the bodies of class templates?
Oh, so the question is whether this technique is applicable also for static asserts in the bodies of classes. So I try to avoid those. I try to move static asserts that I had static asserts in classes. I still have some of them, but they're all not necessary anymore due to the interface that I've chosen for the library. So I have a bunch of factory methods that return objects of certain types, and the static asserts are being moved into those factory methods, and the classes themselves don't have anything. If somebody creates or constructs these classes on their own, and then runs into horrible compile time errors, well, basically that's their fault, or their problem. The interface of the library says, please use one of these factory methods, and then the factory methods are protected with static asserts, which are then testable. Otherwise, other techniques would be to move stuff into the constructor. Constructor is probably not that easy. Maybe you would have to have some function that you call from the constructor for this to happen. But you could probably also do a few things with specialization, but I would have to think about this a little bit more. The short answer was what I gave initially. I try to avoid having static asserts directly in the class body. All right, cool. If there are no more questions, then thank you very much. Oh, sorry.
Could const be used to pass these literals around? Const functions?
If const expert functions could be used to pass this the rep static assert around, you mean? Yeah, I mean, if you get it constructed, well, depending on which version you're referring to. So if you get it constructed somehow, then sure, you can pass it around. It's just an object. And as long as you don't touch the function, either the constructor or the this static function that was used in the const expr if thing, you can just pass it around. It's one of the use cases within SQL ++11 that you can pass this this type around. Could also pass the object around. This way you can transport static asserts to the library interface boundary. So if you have some static assert that is way deep into your template metaprogramming nonsense that nobody will understand except for you, you can use these rep static asserts to basically propagate the static assert to the interface boundary, so that it's very close to the call side, ideally directly in the function that the user was calling, so that the error message that the compiler generates is as short as possible. Yo.
So in your previous talk about improving the error messages on SQLPP, it sounded to me like you were complaining that the compiler didn't stop spewing out error messages when the static assert filed. Yet it sounded like in this talk you thought that was a desirable feature. So have you made a decision on that, or was I wrong? And if you think that's wrong, have you submitted bug reports to the Clang and the GCC folks yet?
Okay, so the question goes in several directions at once, I think. But so the question is whether it's good or bad that the compiler carries on, because sometimes it does, sometimes it doesn't. It's not always beneficial either way. So I don't know. When I first saw this behavior of the Microsoft compiler, I thought that's absolutely terrible because it swallows information that is really, really important. On the other hand, in many cases you wish for less spew from the compiler, so sometimes it's really cool if it stops producing all this nonsense. I haven't filed a bug yet. I don't know, because it's legal, it's a bit hard to file a bug for that. I mean, on the other hand, the behavior is quite inconsistent, so maybe I should. Maybe it would be a nice feature for compilers in general to tell them, okay, well, once you hit a certain kind of error, so for instance, the static assert, just stop. It doesn't make sense anymore. Maybe there should be a flag for that, but I have no idea how complex this is. So, I don't know, maybe one fine day I'll talk to Chandra about this. All right, if there are no more questions right now, then thank you very much.